Hi everyone, I'm Chris, an applications engineer with Cadence. Thanks for your interest in our software and for taking the time to view this. Today I'll be talking about our network synthesis wizard, which is a feature in the Cadence AWR design environment. We introduced the synthesis wizard in version 14 of our software. That was in 2018. Version 15 was released in early May of 2020, so just a couple months ago, and it contained updates for the wizard. Most notably, the capability to use actual component models for the synthesized networks rather than idealized components. So the first portion of this presentation will be reviewing our approach to network synthesis and how we see it fitting into design flows. And then we'll go into the details of how to use actual component models in version 15. So with that said, as an introduction, let's start with a few quick points regarding how we see network synthesis fitting into design flows. It can be used for a wide variety of RF and microwave applications, including high power amplifiers, LNAs, conjugate matching problems, whether they be broadband or multiband problems. We have an example of a multiband antenna match we'll be using in a few minutes, and also an interstage matching where you've got complex impedances on both sides. So all of those problems can be challenging and time-consuming, and synthesis can help streamline those processes for you and enable you to quickly explore a wide variety of candidate matching network topologies. As mentioned in version 15, now you can use vendor library components directly in the synthesis, as well as process design kit, PDK components. So instead of synthesizing with ideal components and then replacing them with the actual models, post-synthesis you can do direct synthesis with the models themselves, saving more time. And we do believe this is useful at the beginning of the design to determine or quantify what are the realistic performance limits or performance targets that you can approach. So a few notes about the specifics of our approach. We are taking advantage of recent advances in computer processing power and algorithms as well. And more specifically, we can evaluate around 10 million circuit responses per second on a modern PC. So we're taking direct advantage of this. We do use a variant of genetic optimization for the underlying search, for the actual topologies, as well as for the parameter values. And this particular algorithm has proven very effective for circuit design problems. So, of course, exactly the type of problem we're trying to tackle. Now, continuing with a few more details, in the wizard itself, the user decides which elements to consider for the series and shunt slots in the matching network. And then we effectively expand and explore all the possible solutions up to the maximum number of sections. So note that this maximum is another user input. That is, the user gets to decide what's that maximum number of matching elements that you're willing to consider. We do have practical considerations that we take into account. For example, you can have stepped impedance transmission lines. That is to say, a series transmission line can follow another series transmission line, but we're not going to have a series cap follow another series cap. Other practical stipulations that could be taken into account: DC open and short paths, component limits. Of course, in the case of using the component models, you get to decide exactly which models to use. You can take into account the impact of bias and feed networks on your match. So if you have a bias network and you think it's going to impact the in-band performance, you can take the presence of that bias network into account when you synthesize your candidate networks. And also constraints on the first and last elements can be placed. So if you're dealing with packaged parts and you need to mount the part on your board or your module, you can stipulate that the first or last element, for instance, would be a microstrip. So again, quite a number of real-world stipulations can be put in place. And so at each stage, we simply sort the solutions from best to worst for each expansion. And we do give the user control over the threshold for which solutions are considered to push into the next search expansion. And that allows the classic trade-off between search speed and overall search depth. And of course, the overall result, what we're going for, is an extremely comprehensive search. Again, taking advantage of that processing power in the algorithm itself. So that was a quick review of our approach to network synthesis and some of the search details. Now let's move on to what's new in version 15. If you've used the wizard before, this user interface should look familiar. And we're focused on the Components tab of the wizard GUI, and you note that we've added some new checkboxes under the series and shunt components for search. Specifically, we've added vendor library, inductor, capacitor, and resistor. Note for the example I'm going to show, we're only using vendor library, inductors, and capacitors, but you can use resistors as well. You get the maximum number of sections up here. That stayed the same as before. And how do you select which components you want to use for your networks? Use the Select Components button, obviously, and that will bring you to the next GUI. And if you've used Microwave Office, this should look familiar as well. It's basically the Elements browser, the bottom of the Elements browser, the Libraries tab that we've brought into the synthesis wizard. So you just expand the Libraries tab, search on down to your vendor of interest or your part type of interest, select which specific components you want to use for your matching problem, push them over to the right-hand pane here, and then you would have a tab for capacitors, inductors, and resistors, and select which components you want to consider for the use of the checkboxes. And that's it. Those models will be part of the matching network search. Also note that you can, once configured, save this to a file. It's an Excel file, and it allows you to, the next time you need to synthesize networks, just load up the configuration. Saves a few minutes there instead of having to do this each time. So you might have a file for vendor A, a file for vendor B, 0402 size, 0603 size, what have you. Also note, if you have a PDK loaded in your project, that would appear here under the Libraries tab, and then it would be the same process. Just expand, find the components specifically you want to use, push them over to the right-hand side pane here, and make sure they're selected, and those will be used for your candidate networks. So moving on to the example problem we're going to show. It is an antenna from Fractus. Fractus is an antenna manufacturer popular in the IoT space. And we've got the raw antenna performance shown here, basically the return loss, and more specifically the magnitude of the S11. We're trying to match for two bands, low band 824 to 960 and high band 1.71 to 2.17 gigahertz. And we can see for the high band we're already fairly well matched. At the low band, not at all. So we're going to come up with a single matching network that is going to improve that low band performance and trade off some of the high band, while obviously not trading off too much performance at the high band. So at this point, let's actually bring up the software. So this is Microwave Office. Obviously, this is the graph that we've captured for the PowerPoint. It is, again, the unmatched antenna with the two bands of interest highlighted. Just want to mention where the antenna data came from. It is a model I pulled in Again, through the Elements browser here, expand the libraries node down to Fractus. We've selected an antenna, and we have a test bench where we've instantiated that file-based antenna model with a couple of subband sweeps to show those, highlight those two bands. So again, just want to show where that antenna data actually originated from. Now back to the project tree, I'll open the wizard instance. And this was obviously, the setup has been saved along with some results. But just want to note the dual band nature of the frequencies to match. You can see our high band and low band components. We have selected those vendor library inductors and capacitors, so we're only considering those discrete element match strictly for this example. And just want to show the goals tab quickly. One measurement, two goals, low band, high band, and you can weight the goals separately. Have sloped goals, what have you. Essentially anything you can do with our native optimizer setup, you can do with the synthesis wizard. We do have results saved. You can sort on component count. I'll sort on cost, get the lowest cost 5 networks here we've put to Microwave Office. You can see a quick pictogram of each topology if you select it. Once you're happy, again, you do output to Microwave Office. I'll go back to the graph and quickly enable a few measurements here that will show now the antenna with the matching networks in place. So we see we are improving the low band performance substantially, trading off a bit of high band return loss, and then I can select the individual networks and see the response update. If you like data displays, and this is automatically created for you. You can customize after the fact, but we've got the same graph, and we can now see a view of the schematic for each of the networks. And we notice that they are, in fact, incorporating the actual lumped element component models. So to finish up, we'll go back to the PowerPoint and just mention that, again, we're using the actual component models for our networks. And you can actually constrain the number of unique library components. So it's bill of material simplification. If you like to do that, again, constrain the number of components. So just one last slide. We do not only, of course, conjugate matching, but we do integrate directly with load pole data. It's a big advantage for PA designers. I mentioned before that interstage matching is supported, noise matching is supported, and a direct Smith chart impedance target matching is supported. And now all those you can use, again, vendor library components with each of these. So with that, I will conclude. We hope you find our updates in version 15 useful, and of course, let us know if you have questions. Thank you.